Hi everyone. Today we're talking about IFIT. IFIT is an in-band flow measurement technology. It measures the quality of service flows by inserting IFIT headers into real service packets. And telemetry is used to report measurement data in real time. IFIT enables you to guarantee SLAs and achieve far more effective network O&M and performance monitoring, and lays a solid foundation for intelligent O&M. IFIT is mainly classified as application-level measurement, which measures the quality of service flows, or tunnel-level measurement, which measures the quality of forwarding paths. Today, we'll look at how to configure application-level IFIT. We'll use L3 VPN v4 over SRv6 networking as an example. In such networking, public SRv6 tunnels are used to carry L3 VPN data. Application-level IFIT is deployed on the network to monitor the packet loss rate and delay of service flows between PEs in real time. This enables adjustments to be made quickly if service quality deteriorates. Before configuring IFIT, you need to configure L3 VPN v4 over SRv6 and ensure that it is running properly. We'll focus only on the IFIT configuration in this course. The configuration roadmap is as follows. To begin, configure a clock protocol so that devices can synchronize their clocks. We use 1588v2 as an example. Next, configure IFIT for the link between PE1 and PE2. IFIT can then periodically collect statistics on the packet loss rate and transmission delay of the transit network. We'll introduce two configuration modes in this course, 5-tuple-based and peer-based. Finally, configure PE1 to send measurement data to the NMS through telemetry. Let's dive into the specifics. Measuring indicators such as the packet loss and delay accurately relies on devices having synchronized clocks. A few clock synchronization protocols are available, notably G8275.1, NTP, and 1588v2. Here, we'll use 1588v2 as an example. Enable 1588v2 on the P and PEs both globally and on their interfaces. Configure PTP-based clock synchronization between PEs, and configure the P to import clock signals from an external bits clock source. Change the configuration depending on which protocol you select. Note that you must deploy the NTP high-precision clock if you want to implement delay measurement. Moving on, let's look at how to configure 5-tuple-based IFIT measurement. This lets you uniquely identify a static flow by specifying 5-tuple-related field information in an IP packet header. The key configuration procedure is as follows. 1. Enable IFIT globally on the ingress PE1 and configure a globally unique NE ID. 2. Create an IFIT instance and then configure IFIT parameters in the instance view. For example, you can 3-1. Set the IFIT measurement mode to end-to-end or hop-by-hop. End-to-end measurement helps monitor the performance of a transit network in real time and detect faults. Hop-by-hop measurement helps locate a performance fault hop-by-hop. Here, we use hop-by-hop measurement as an example. 3-2. Configure a measurement interval for the IFIT instance. We use 10 seconds as an example, but different network conditions and device performance specifications will determine the value you use. 3-3. Define an IFIT flow. You can do this by specifying the source and destination IP addresses, protocol number, source and destination port numbers, and DSCP value. In this example, we create a target flow whose source IP address is 192.168.1.1. Destination IP address is 172.16.1.1, and DSCP value is 63. The flow belongs to VPN A. 4. Finally bind the target flow to the inbound interface of PE1. This wraps up configuring the ingress. For transit and egress nodes, you only need to enable IFIT globally and configure a globally unique NE ID. After completing the configuration, run the display IFIT command on each device to check the static IFIT instance configuration. Take the command output on PE1 as an example. Information such as the flow type, instance ID, flow ID, 5-tuple information, and tunnel type can be queried. This helps you verify the configuration. Let's look at how to configure peer-based IFIT measurement. Peer-based measurement is configured the same as 5-tuple-based measurement, except for the target flow configuration because they differ in how they define the target flow. Peer-based measurement defines a target flow that belongs to VPN-A by specifying the peer SRv6 locator prefix. This method can be used to measure the performance of end-to-end traffic. Binding the target flow to the inbound interface of PE1 wraps up the configuration on the ingress. For transit and egress nodes, you only need to enable IFIT globally and configure a globally unique NE ID. After completing the configuration, you can run the display IFIT command on PE1 to check information about the flow type, instance ID, flow ID, peer locator, tunnel type, and more. Now, let's look at how an IFIT header is encapsulated by parsing real service packets. In SRv6-based application-level IFIT measurement scenarios, the IFIT header is encapsulated into the SRH as a new type of TLV to carry measurement data. FII identifies the beginning of an IFIT header and defines its overall length. The type value is fixed at 130, and the IFIT header length is 22. FIH uses the flow ID field to uniquely identify a service flow. The L and D fields in the FIH respectively provide the packet loss and delay measurement capabilities based on alternating coloring. Here, both fields are set. FIEH identifies the measurement mode, type, interval, and other extended capabilities, such as forward-backward flow, per-packet delay measurement, and packet disorder measurement. 0 is used to indicate the trace measurement mode and the application-level type of measurement, and the measurement interval is set to 10 seconds. For more details, refer to IFIT packet format in the product documentation. Next, we need to configure PE1 to send measurement data to the NMS through telemetry. We can do this in the telemetry view, where we need to 1. Configure the data to be sampled. This involves creating a sensor group and adding sampling paths related to IFIT measurement to the sensor group. 2. Configure a destination collector. Specifically, create a destination group for the sampling paths. Then, based on the collector type, configure an IP address and port number for the destination collector, and configure a protocol and encryption mode for data sending to the destination collector. 3. Create a subscription and associate the destination group with the sensor group. After completing the configuration, run the display telemetry subscription command on each device to check the telemetry configuration. Take PE1 as an example. You can view various pieces of information, including the source address, destination address, transmission protocol, and port number. At this point, we have completed all configurations of application-level IFIT measurement. Let's summarize data forwarding and sending of IFIT. 2 common measurement modes are available: end-to-end and hop-by-hop, trace. The end-to-end mode applies to scenarios where end-to-end overall service quality monitoring is required. Conversely, the trace mode applies to scenarios where hop-by-hop demarcation is required for low-quality services, or on-demand hop-by-hop monitoring is required for VIP services. IFIT supports both end-to-end and trace modes. In end-to-end measurement, an IFIT measurement point needs to be deployed only on the ingress in order to trigger measurement, and IFIT needs to be enabled on both the ingress and egress. In this case, only the ingress and egress are aware of IFIT packets. They respectively encapsulate and remove the IFIT header into and from packets and report the measurement data. Transit nodes directly forward the packets. In trace measurement, an IFIT measurement point needs to be deployed on the ingress in order to trigger measurement, and IFIT needs to be enabled on all IFIT-capable nodes along the service flow path. These nodes forward and report data. Based on the configuration requirements, PE1 collects measurement data, such as the flow ID, flow direction, interval, and timestamp, and encapsulates it into telemetry packets for reporting to the NMS. The NMS then analyzes the data and displays the measurement result on its GUI. Typically, end-to-end IFIT and trace IFIT are used together. When the end-to-end IFIT measurement data reaches the threshold, trace IFIT is automatically triggered. In this case, the service flow forwarding path can be restored and faults can be quickly demarcated and located. That's all for today. Thank you for watching.